Hey, good morning to my wonderful students. This is Dr. Manis. Just a few minutes about pKa. pKa tends to be difficult for students to grasp at times because I think the P intimidates you a little bit. Don't let it intimidate you. Just be fluent. P means negative log. So when you see pKa, just read it as the negative log of the Ka. When you want to get a Ka from a pKa, all you have to do is take the negative log of the Ka, sort of undo that negative log. Move the negative over the 6.2, raise it to the power of 10. Logs are exponents. You just undo the log. If you can't remember that, on your calculator, there's a log button. Right above the log button, it says 10 to the x. So you can always remember that, hey, to undo the log, I hit 10 to the x. Okay, not a big deal. You really just hit second log or inverse log, depending upon your calculator. The big deal is interpreting what a pKa is. pKa's really come at us from the Henderson-Hasselbalch equation. So I set up this example with acetic acid and acetate. If you notice the amount of acetic acid, the concentration of the acetic acid and the acetate are equal. And that's going to have a special impact in the Henderson-Hasselbalch equation because now you're going to have this term, the A negative over HA term. These two values are the same, so it's going to cancel out, become 1, log of 1 is 0. So we end up with this special instance that the pH equals the pKa. That occurs when the concentrations of the acid and the base are equal. Another way of looking at it, it occurs when, if you remember, the acid is reacting with something like water and forming the base and hydronium. Well, for A negative and HA to become equal, that means 100% of HA has become 50%, while the other 50% has become A negative. So a lot of the ways you'll see it in standardized testing and on tests is that the acid, 50% of the acid has reacted. Well, 50% of the acid reacted is code for saying you're at the pKa. So what's the significance of this? If pH is less than the pKa, then if you look at the Henderson-Hasselbalch equation, you're going to end up with this groovy little stuff I'm highlighting there, and I won't say all of that. Negative log values are going to be the log of A negative or HA. Basically what it means, when the pH is less than pKa, concentration of the acid is more than the base. So the HA is present. That's huge. When pH is greater than the pKa, then A negative is more than HA, and the base is present. So at a higher pH, higher pHs, you get bases, lower pHs, you get acids. That kind of fits with the pH scale. Get the idea of neutrality out of there. The pH scale talks about acidic and basic. What we're saying is acid and base, slightly different. Let me just put this into context of the pH scale and we'll be done here. If you look at the pK being 4.7, so let me slap that in here at 4.7. That means at a pH less than 4.7, we have acid. If we are at above 4.7, we have the base, in this case, the acetate. And for the acid, it would have been the acetic acid. A lot of chemists, myself included, will talk about the protonated form and the deprotonated form. Protonated means it has the H on there, the proton, and deprotonated, the base. Alrighty. So basically, generally speaking, for any acid, HA, less than the pKa, you're in HA territory. Okay. Above that, pKa, you're in the base territory. So let's pretend the pKa, say, I don't know, 8.5, man. Okay. That's our pKa. That means above 8.5, we're going to be basic, be the base form. Below 8.5, we're going to be in the acid form. This comes up in titrations a lot when we deal with what we call indicators. Indicators are these things that you put in that change color with pH. If you ever worked at a pool or seen lifeguard at a pool testing the pH of the water and making the color change, they're using an indicator. Okay, so the indicator has a special color when it has the proton at their big molecules. When they're protonated, they have a color. Let's pretend this one's red. When they're deprotonated, they change color because of the formation of the charge. Let's pretend it's blue. So what this means is that at pH above 8.5, we're going to be blue. And at a pH below 8.5, we're going to be red. So if you were doing an acid-base titration, which is new to you now, but won't be in a few class periods. But if you're doing an acid-base titration, starting off at a low pH and moving on up, that means you're going to start off red and then end blue. And in acid-base titrations, what you're really looking for is this special little middle ground where you're at the pKa of the indicator. That's going to be a special little point in that titration curve, which we'll talk about in another video, but that is just a blending of the two colors of the indicator. In this case, red and blue, which would make purple. How do you know it's a blending? Because we are at the pKa. The pKa is when you have the HA and the A negative. You have both forms in equal amounts. So if you have both red and blue in equal amounts, you would have purple. So to recap, pKa, pH less than pKa, HA is present. pH greater than pKa, base form A negative is present. That's it. Hope you like it. Hope you learn it. Have a great day. I'll talk to you later.